Welcome to what I gather is the last of this season's, too short, the last of this season's set of UCL lunchtime lectures, though I gather they will be restarting in October. Today's lecture is on pigments in art and archaeology by Professor Robin Clark. Now, Professor Clark has led a long and distinguished scientific career. He was born in New Zealand and has been a companion of the New Zealand Order of Merit since 2004. After taking his first and master's degrees at Canterbury University College in Christchurch, he first came to the UK in 1958 to undertake studies for his PhD in chemistry at UCL. And he's remained at UCL ever since, although he has managed to fit in lecturing at over 350 other universities and institutions in that time, and also acting as visiting professor to 13 other universities. Besides all this, he is a fellow of many major institutions, including the Royal Societies both of this country and New Zealand, and he served on the councils of the Royal Society, the Royal Institution, where he was secretary for 6 years, and the University of London Senate, and has received awards too numerous to go into. Although he's now officially retired, he has in no way slowed down, as this lecture will show. Professor Clark has long been interested in molecular spectroscopy. In 1969, he brought to the first laser Raman spectrometer to UCL, and he's been very heavily involved in the development of this technique. Raman is now something which is very widely used throughout industry and chemistry, but much more importantly to all right-minded people. It's used extensively in museums. We have had a Raman spectrometer in this museum now since 1999, and you'll see examples of some of the work that we've done with it in the Treasures of Heaven exhibition, which is open at the moment in the Round Reading Room, and also spectra in along with some of the Chinese jades. Professor Clark was a pioneer at the introduction of this technique into art and archaeology, and that's what he's going to be talking about to us today. So with that, I'd like to introduce Professor Clark to talk about Science Meet Art, investigating pigments in art and archaeology.
Thank you, Janet. Good afternoon, everyone. When you look at a piece of medieval artwork such as this, with intertwined figures, great design, strikingly coloured, you always admire it as a piece of artwork. I want to try and convince you that it's also excellent science behind all of that, because when you think about it, all the colours are pigments. The pigments from most periods of time were inorganic pigments, minerals, or synthetic inorganic materials. And so you did need to know chemistry in order to be an artist, and the early artists did know a lot of chemistry. They knew that in many cases if you put A next to B, they would react, and so they didn't do it. So they had to know chemistry. So I want to try and persuade you that this is a branch of chemistry. So what is the purpose? And pigments are the key to it. So what are the purposes of looking at pigments and identifying them? Well, the characterization, what pigments did an artist use? Did he use a single one or a mixture? And all sorts of questions of that sort. Questions to do with restoration, repair of damaged areas. Have there been any changes in colour with time? Anything to do with conservation? What are the effects of heat, light, and gaseous pollutants, and such like? And the vexed question of authentication, which is linked into the assignment of a probable date to a work of art. So what are these pigments? Well, there are several hundred of them, increasingly fast now. It isn't possible to go through all of these, but just by way of illustration, I've just listed up the 7 most common blue pigments used, And there are also at least 20 others that are in widespread use, which are blue. But this is the sort of information which is readily now available. We know what the chemical name is, the formula. We know the origin of the blue color in each case. It's different for different pigments, and that's a branch of inorganic and physical chemistry that was heavily studied in the 1950s and 60s and 70s to find out from where the electron was going and to where it was going in the molecule. And it was always going to be in the red, absorbing-wise, if the thing is blue. So we know all about the origin of the color. And this column simply lists whether something is a mineral or whether it is synthetic. And if it's synthetic, I've listed the year of manufacture. Prussian blue here, 1704. Copper thallocyanine blue, Manchester, 1936. So the message I want to get over is that if you find Egyptian blue on an Egyptian papyrus, supposedly dating to 1250 BC, that's bad news for the papyrus. Now, the technique I'm talking about is something known as Raman scattering. Now, you may or may not wish to know about this, but you're going to get one slide anyway. It goes back to Lord Rayleigh, who in 1870 was the first person to realize that if you took a beam of light of one color, one frequency, and shot it, he was interested in gases, there is most of the light goes straight through because it misses the molecules, but some of it strikes the molecules, and the molecules re-radiate the same frequency in all directions. It's a very weak effect, and it happens to relate to the fourth power of the frequency that you used in the first place. That means blue scatters better than red. Now, we're all well conscious of that because it is Rayleigh scattering from molecules in the sky, which makes the sky blue. The molecules of oxygen and nitrogen and what have you, they scatter much more effectively in the blue, and they scatter in all directions to make the sky blue, so that when the sun sets, it doesn't all go black instantaneously. So Rayleigh scattering is well known, but it's not in a molecular sense very useful. We had to wait until 1928 and to C.V. Raman in Calcutta, who made the key discovery that it wasn't just the original frequency that a molecule scattered. It's the original frequency plus or minus some other frequency related to the molecule. And in fact, what I'm going to be talking about is what's called the vibrational Raman effect. That is, you see plus or minus little side bands. You've got the Rayleigh line here, and then in pairs going out, you see these sum and difference frequencies, which relate to the vibrations of the molecule and so are highly specific to the molecule. They really do act as fingerprints of what you've hit. So I can shoot this beam at anyone's top over here. I won't do it, but this man's greeny blue top there, and the signal will come back telling me exactly what pigments he's got in that. I mean, I haven't got the detecting system, and that's what's tricky, but that's the basis of it. How do you do it? Well, in Raman's day, he actually used sunlight, which is not monochromatic, not single frequency, and he, as his detector, he used his eyes. Well, this was a proof of principle experiment he did. To do anything quantitative, you've got to have single frequencies, and you've got to have a really good source, a high power density source in watts per square meter. And of course, we've gone from the eye to photographic plates to all sorts of lasers and things, and increased the power density by many orders of magnitude. And then in terms of detectors, the use of the eye is extremely limited, and we've gone to many other sorts of detectors, finally to something which is shown here as a CCD detector. That means charge-coupled device, something designed by physicists in order to see stars in distant galaxies. And that will give you an idea of this fantastic sensitivity that is on the modern Raman detector. So this is the sort of system that much of what I will be talking about looks like. The laser beam comes in the back of this instrument, shoots along here, is filtered so there's only one frequency comes here. We link it to a microscope so it's then deflected down there to the stage, and that's where you put the sample. It then Rayleigh scatters back up here, comes right through this optical system into the CCD detector, which then tells you what these sum and difference frequencies are, and you then go to a library of Raman spectra, which we and other people have developed so that this can all be looked at and identified. Well, we first looked at anything artistic sort of 15 or more years ago when somebody brought us a little thing of this sort here. This is an historiated letter R, which you can see here. Here's the R. Historiated means there's a story being told in the middle of the letter R, and the letter R is the first letter of the first word on a page. And the question was, I mean, this is obviously the Archangel Gabriel bringing good news to Mary, but the question that we had was, what were these two blues here? That's what the library wanted an answer to. And we could tell them very quickly that it was the same pigment, azurite, a copper-based carbonate. And the difference in depth of color simply related to particle size. The pale is 3 micrometer-sized grains, and the deep blue is 30 micrometer-sized grains. And then we could run through, and that we looked at these. That's malachite, that's basic white lead, basic lead carbonate. This is vermilion, mercury sulfide, and the yellow is a lead tin yellow. We also looked at the black, and that's revealing in some interesting way, because we had assumed that that would be carbon black, a single material. But in fact, it's actually a mixture of different pigments, each one of which absorbs light in a different frequency through the visible, so you get the net effect of being black by having this mixture. Now, I don't know why someone would do that, but that's what, in fact, they had done in this particular case. And this also shows the benefit of coupling the Raman system in with a microscope, because you can look at these. This is obviously a pigment mixture, and you can move across, you see, and come onto every pigment grain and tell what each component is. And the spatial resolution is about 1 micrometer. That's 1/1,000,000th of a meter. So you can go onto that yellow grain there, which is about 2 micrometers across, get the signal back from that, and it's not interfered with by all the other pigments around about. It's a very good, that's what we mean by spatial resolution. The laser beam will focus onto each pigment grain in turn, and you can find out what each component is. And most techniques won't go anywhere near doing that. The Raman spectra themselves look something like this. And this is another very early one that we looked at, a Paris Bible coming from the Czech Republic, in fact. And here we have azurite, orpiment, lapis lazuli, realga, lead white, red lead, malachite, and vermilion. That's 8 different, very common pigments. And as you see, each of these is what we would call a Raman spectrum. That is a listing, a sort of scanning of all the frequency differences. And so if you see down here, the Rayleigh line is somewhere near the edge here. It's been cut off the figure because Rayleigh is a much more effective scattering business than Raman is. So you don't want to take the detector anywhere near the Rayleigh line, otherwise you're liable to kill the detector. So coming up quite close to actual zero would be the Rayleigh line, except we've cut it off from there. These other peaks are the difference peaks. I'm not showing the sum, but they come out, as I said, like this in pairs. And these are characteristic of the compound you're looking at. So there's 8 pigments there. Every one of these spectra is different from every other one. They're easy to get, and so they define what the pigment is uniquely and quickly, and they do it with great spatial resolution and so on. And it can be done in situ. Of course, you can also look at pigment grains if someone can bring those to you, but sometimes you have to look in situ, and you can do that under this microscope system. Well, many of the pigments have several books written about them. I mean, this is a big and an old business, writing about pigments. I actually, long before paying any attention to artwork, I was intrigued with lazurite 40 years ago, wondering why it was blue. Well, this is the mineral lapis lazuli, which comes from a very remote part of Afghanistan in the hills. And that's the mineral. The blue part is what's known as lazurite, which is the intriguing part, which is extremely valuable, was worth more weight for weight than gold in the Middle Ages, because of the brilliance of the blue color and the permanence of it and its stability up to high temperature. The rest is calcite or something like that, and then there are flecks of iron pyrites in there, slightly brownish, and there are a few other trace impurities in it. The whole history here related to the very difficult extraction business to get hold of the mineral lazurite out of lapis lazuli. There was not enough lazurite in the world for the artists, and that's why it was so highly priced. And the French government offered a prize in 1824 to anyone who could make it. People knew it was a sodium aluminosilicate, which is only one step removed from kaolin, which is known and prized because it's white, and you make China clay it is. So they knew essentially what it was, at least 99.5% of it. And there's a little bit of sulfur there. Well, that's the bit that intrigued me 40 years ago. Sulfur is obviously yellow, so it isn't sulfur itself. And after quite a lot of research, which I won't go into, we turned out that the chromophore, that is the thing that's trapped in the cubic cage of lazurite, is S3-. It's a SSS. It's a bent sulfur species, trinuclear species, carrying one negative charge. And it's found in a few other places as well, in crystals and sometimes in melts, when you melt potassium thiocyanate. So we know what that's caused by, and if you go into the business, you can actually make it. That's the synthetic form, which is known as ultramarine blue. There is also ultramarine green, violet, pink, and an ultramarine selenium when you get other radicals trapped in the lattice. So all of that is now known about. Ultramarine blue was made in Hull for well over a century, and they've now sold out to the French, actually. It was a big business when I was a boy, I know, because you didn't have proper washing machines then. You had a copper, and the clothing that went into the copper always had Dolly blue or Reckitt's blue in it, and that's a little muslin bag containing precisely that, the synthetic form of lazurite, and they made tons and tons and tons of it. And that's just went in and got entrailed in the fabric, and by a complementary optical effect, the yellowing of the whites, that was complemented by the blue of the ultramarine blue, the Dolly blue. They may still put that in some washing powders, actually. I'm not sure now. Now, I don't want to develop onto stories about the pigments, but there are vast volumes on all of the pigments. Let me turn to some of the things that we've looked at in recent years, so that I know what we've so you know something about what we've looked at. The Lindisfarne Gospels. Is this, can I just check the time? Yes, okay. The Lindisfarne Gospels at the British Library are this wonderful bit of artwork made by Bishop Eadfrith in honour of St Cuthbert on Holy Island, Lindisfarne Island, back in 715. A fantastic piece of work. It took him 6 years to do it, and it's absolutely brilliant artwork. You can see it yourself if you wander in on the ground floor of the British Library. This is Eadfrith's copy that he made. It was a copy of the St. Jerome's version of the Gospels, and this is actually the prefatory page. And I'm no Latin scholar, but with my hand held, I can read two words, and it says Novumopus, new work. I can't go beyond that, but there are plenty of experts who will take you well beyond that. I just want to emphasize that this is a wonderful piece of artwork, brilliantly colored, and there are many curiosities about it. I mean, it was translated also from the Latin into Old English 240 years after this, 715. And there you can see the translation written here. No, that's known as interlinear gloss, interlinear between the lines. Gloss means translation. I think it was controversial when that was added, but it probably isn't now, probably regarded as interesting. So this is the Matthew, Mark, Luke, and John, and it's brilliant artwork. We had a look at that at the British Library, and I'm not going to go through all the pigments that we found, but I was more interested in the one that we didn't find, because the British Library had a label up saying some detail about lazurite and showing where it comes from and everything. And that was the only pigment they mentioned on the card in front of the actual Bible. Actually, that's the only pigment that is not there. When we looked at it, it was quite clear that this was indigo, which you extract from woad, and is well-known and grown, and has been for 1,000 years or so in England, especially on the eastern side. What was there was definitely lazurite. It was definitely indigo. It was not lazurite. And when you come to think about it, it was going to be incredibly difficult to get hold of lazurite. I mean, did the monks really know it existed? How would they have got it from the Hindu Kush mountains up to Northumbria in 715? It beggars belief. But that's the sort of strange information found there. We looked at the Tours Gospel, 825 AD. Now, this is actually the cover. It's an oak cover. It's got an embossed silver front to it. It's got enamel in the corners, and it's got gemstones, 12 of them, all around the outside. The interest there is in what the gemstones were, because it was realized that in past centuries, there have been some light-fingered inspectors and lookers at the gemstones who brought in a pocketful of coloured glass and sort of substituted the gemstone with coloured glass. They didn't know what's happened here. Well, we still don't really know, but we've looked at those. There are only 4 different stones there. There's amethyst, emerald, iron garnet, and sapphire. They're still there. Whether they were the original ones, we don't know, but at least there's a marker now if anyone wants to substitute those for coloured glass. We've actually looked at 8 Gutenberg Bibles, or pigments from them. These Bibles also on view, and very easy to see at the British Library. Gutenberg ran these off. He was the first one in Europe to use movable and reusable type. He made about 180, about 48 survive. And there were model books which said what pigments people ought to illuminate this with. because Gutenberg ran off, as it were, the black and white copy. You bought that from him. If you wanted it illuminated, you had to find yourself an artist, and then he wanted payment for all the pigments. So you had to decide whether you wanted to put the most expensive of all, lazurite, on it or not. Well, this particular one, the one we studied in greatest detail, also you can see in the British Library, is the George III copy, which went in about 1828, and it's superbly illuminated. It's got images of foliage, flowers, birds, and fruit calling around the main body of the columns, which you can see here. I mean, this is absolutely brilliant artwork. Well, we have looked at that, and of course, these are big volumes. I mean, they're 25 million pound jobs. You've got to be very careful with them, and you can't go sort of trying to bend the back open a bit more to get it under a microscope. You have to design the right sort of equipment which will hold it at an optimum angle, and then use a mobile Raman spectrometer, such as this here, and that's a laser which shoots down onto the page, and then you collect the light back from that, and that tells you what pigments are actually used. Well, this is what we found on that particular one. We've looked at 8 of them from different parts of the world, and there are at least 2 others in the UK, one at Eton College and one at Lambeth Palace, and we've seen the pigments from them too. So we're still working on this, trying to compare whether the palette used was always the same from one Gutenberg Bible to another. You could also look at paintings. I mean, water paintings are quite easy to look at. Ones that might have any varnish on them are much harder because the varnish fluoresces, and that's a competing technique. But one did turn up in London in 1995, and I can't go into all the history of this because it's big, but Vermeer's had particular problems with them because of 1947, someone was convicted of forgery in Holland who apparently made about 7 Vermeers, which the experts couldn't identify and thought they were Vermeers. So any Vermeer which didn't have an absolutely perfect history to it, such as the ones that have been in museums and libraries since the year dot, or in Buckingham Palace or wherever, there's no problem with those, but ones where there's a little gap in the knowledge about where they were held, anything of that sort, had a bit of trouble after 1947, and this was one that came up in that category. And Libby Sheldon at UCL History of Art looked carefully at that for many years at that with some of her assistants, and we had it at one stage just to look at too. And this shows that Vermeer under the microscope of the Raman microscope, and easily you can see how one could track around there and see what pigments are. There are actually only 2 which really matter, which were lead tin yellow type 1 and lazurite, which are consistent with its being a Vermeer. And this is one of the problems in this kind of work. If you find something that shouldn't be there, that rules it out instantly. If you find things that should be there, well, okay, that's fine. It doesn't prove anything, but you've then got to do a whole host of other measurements to see whether you can establish it, as it were, beyond reasonable doubt. Postage stamps are another form of artwork. There was one, we've looked at Mauritian stamps and these Hawaiian ones. The Mauritian ones, 2 days ago in the Times, there was a photograph of an 1847 Queen Victoria head blue tuppenny stamp. That went for over £1 million. So So that you do realise that the postage stamps are worth a lot of money if they're rare, and it's worthwhile trying to forge if you're any good at it. Well, the Hawaiian missionary ones were in that category of 1851, and there was a group known as the Grinnell missionary stamps, which were judged in 1918. 43 of them were sold, but they're judged to be forgeries. 55 turned up again in 2002 in London at the Royal Philatelic Society, and we linked in with them to have a look to see what we could see. Could we see any defining feature which might show that they are? Oh, well, that's the stamp that was photographed in the Times 2 days ago. That went for over $1 million. This is the Hawaiian missionary stamp that we looked at with some care. It's a 13-cent stamp shown here. The blue is Prussian blue, and then many of the other colours are to do with the franking, the reds, vermilion and hematite, and there's carbon black there also. And there's nothing wrong with that. That wouldn't tell you whether it's a forgery or not. But we looked at a cross-section here, and so the stamp, this is the edge of the stamp. It's been sliced through, and that's the edge. And on this side is the Prussian blue. And this is the fabric of the stamp. And what we discovered over here was a small grains of ultramarine blue in the genuine ones. And so the stamp maker had put ultramarine blue in as an optical brightener because paper yellows with age. And so if you put in the first place some complementary colour, and ultramarine blue is the ideal thing, that's what actually happens there. The forged ones, as far as we could see, never had the ultramarine blue in. Now you can move across and look, and we have studied a large number of icons of this sort. This is Saint Athanasius of Athos, Mount Athos, in a really bad state of repair. Mount Athos is on the far eastern corner of Greece, sort of facing the Dardanelles. Has 43 monasteries there, and hasn't been a female there for 1,000 years. I'm not sure what you read into that, but there's not been a cat either. But I did go there one Christmas, and if you really want to see monks driving 4x4s in black capes and hat up snow roads, that's quite an experience. But the actual churches are left quite wide open, and so anything hanging in these churches has quite a lot of exposure to the elements, and they do degrade badly. You can see this one has had a terrible time. It's been overpainted, and even some of the overpaint has fallen off. And you can shoot a laser beam down in various places and see and track and see what the pigments are at different depths. You could also take samples, cross-sections. And this is a cross-section of the Saint Athanasius one. And if you look then, this is the wood. That's the original painting, that layer. Then there's a white layer, a kind of ground layer. Then there's the varnish layer, and then there's the overpainting. Now, through all that mess, you can learn some things. That red crystal there gives this spectrum, which is caput mortuum, as a form of iron oxide. The blue gives this spectrum, which is azurite, a copper-based carbonate. Then there's a lot of white material there, which we've identified. Then there's the varnish, and then up here, the 3 gives you this spectrum, which is carbon black. And then up here, the 4, that is zinc sulfide, in the form of lithopone, which again is a modern pigment. You'd expect the modern ones to be on the overpainting. So we can tell them what's there. Of course, it's up to them to decide what they want to do, whether to restore the surface painting or take it all down and restore the original painting. I suspect that many of these icons are in such bad order that they can't do any restoration at all. You can also look further at other things, archaeological treasures. And it so happens that the V&A Museum has a vast, several hundred items from Samarra, which sort of collapsed around 892 AD. And all the wonder of Samarra was buried for 1,000 years or so until certain experts went out, German experts went out, and brought back to Europe several thousand items of broken ceramic work. And the V&A Museum got about 300 of these, and they've been crated up for almost a century. And we managed to get the first look of these just 2 years ago. And you see, these fragments are, because they've been buried and suffered no damage after they fell apart, they're actually in very good order, and it's no difficulty in identifying what these pigments are. And they turn out in general to be more or less the same pigments that are used in artwork. And there's no end of experimentation that could be done there at the V&A if they wish to do it on the other 300 or so things they have. And they also passed on to us a stucco fragment from the Alhambra, supposedly Nazareth plasterwork of 14th century. So we had a look at that, and especially at the blue in these grooves here. And that is unambiguously Prussian blue, first made in 1704. So the only thing we can tell them is that either this is a replica or it's been repainted. And so that part is certain. We can't tell them more than that, because it should have been lazurite. Would originally have been lazurite if you go through Granada. There's some other things which are much more obviously forgeries. I had a bunch of 4 Egyptians come and see me once, and it turned out, and again, this is a sort of dinner table conversation, because it's quite a long story and very funny in parts. But these 4 Egyptians, at the end of the day, wanted to sell 100 papyri at £2 million each in London. And this is one of them. And that's another one. And I had a quick look at that white worried me. And I had someone, Lucia Bergio, who actually works at the V&A. She was very keen to look at papyri. UCL wouldn't give us any at that stage. They had plenty. So we had a look at this one. And it has gypsum, red earth, and calcite on it. No problems. They're minerals. You'd expect that. It had anatase on it. Well, anatase is a mineral also, but as a mineral, it's always deeply colored. It's either black or deep blue or can be brown, all sorts of things. I've never seen native anatase white. We are surrounded by it normally. There'll be even the back here will be anatase because it's number 40 chemical in the world. Always in paint, whatever the color, because it scatters light extremely well. And they sell it from how white they can make it. Well, that white on Nefertari's dress was very white. We looked at it, and we know from the pigment grain size and everything that that is certainly synthetic. They were unimpressed with that information, but they were even less impressed the fact we found about 7 other pigments which were also modern, including the thalocyanine blue, 1936. It's not 1250 BC. And that's what the Petrie Museum ones look like. I mean, they're brown because they're mainly iron oxides. you'd think I'd never look at another papyrus, but I did have a friend in the States call me a few years ago and say, look, he'd been to Luxor and bought from a very, very posh-looking shop quite a nice papyrus, and he was thinking of leaving it in his will to his son, and he was going to fly it over from the States. Well, he did do that, but we didn't even need to get that one under the Raman microscope, although that certainly confirmed it, because we got it under an ordinary microscope, and that had rows of yellow dots, rows of red dots, and rows of blue dots. It was clearly the product of an inkjet printer. So I had to advise him he probably didn't need to mention it in his will. So I'll just finish with one other example here, the so-called the Spanish forger, who was extremely successful. What was forged was George Inglé, a 15th century Spanish painter who was greatly admired. And they started getting suspicious because there were too many of them in circulation and coming up for sale. And if you look at them, you find that they're all on medieval musical pages. At least one side is musical notes, staff lines and initials, and but definitely medieval paper or vellum and what have you. When the other side was scraped clean, and he'd do his forgery on that side. And by about 1950, they were realizing that on stylistic grounds there was things wrong, and there were quite a lot of these about. The V&A Museum bought 5 of these only about a couple of years ago, and we were lucky enough to have a look at them. Now, they're actually very attractive. I mean, the chap made a really good job of them. And you can see there are the 5, and this is the verso with the medieval inscriptions still on it. They're there, and there's no problem with this. But if you actually put these apparent forgeries under the microscope, what you find is this. There are some undateable pigments, but there are 4 modern pigments. There's chrome yellow, 1809, Shields green, 1775, emerald green, 1814, ultramarine blue, 1828. These 4 are signatures of something post 15th century. And so nowadays, if there are any more of these crop up, you just put it under a Raman microscope and you will find these 4 pigments for sure. So that's the first scientific investigation of these. I'll just finish to show you what happens when something goes wrong in the atmosphere. This is also at the V&A Museum. Pair of dividers here, German, watercolor, 1585. What's happened to that hand? If you look more closely at the hand, you'll see that it's all blackened, and that the parts that would be brightest, high lit as it were, are the blackest. And if you look at the black, it's lead sulfide, and it's so what the artist did would make those the whitest part with basic lead carbonate. But there's been hydrogen sulfide around, either from the atmosphere or from bugs eating up the sulfur-containing binders and generating hydrogen sulfide. So that's a really bad example of what can happen in degradation circles. And this seems to be about the ultimate, that this particular one where goodness knows how much hydrogen sulfide got around there to attack the white lead. So I think that just gives an idea of this particular way in which science now impinges on artwork.